Hello everyone and welcome you all for today's class. Yesterday we have discussed about stream function and its physical significance. As you know that a stream function is very important, and stream function and velocity potential are complementary to one another, and both one can be determined with the help of another. So today we are going to discuss mathematical function, another mathematical function, that is a velocity potential. It is again a mathematical function, but it is as a stream function. It is also very suitable for defining flow phenomena in flow field, velocity or position of the fluid particle or acceleration field, and the type of flow, whether it is a circular flow or irrotational flow, rotational flow. All these phenomena can be defined by the velocity potential. Both in combination with velocity potential and stream function, we can define flow net, which is very useful in defining flow phenomena of very complex type of flow, because when there is a complexity in the flow channel, we can better interpret types of flow, pressure variation and velocity variation by the help of flow net, and flow net can be drawn with the help of velocity potential and stream functions. These are very important things from completion point of view, and in order to understand kinematics of fluid flow, and further when we go for the dynamics of fluid flow, these concepts of kinematics will be used and will be helpful in analyzing dynamics of fluid flow and different types of flows in a pipe. So let us start. Let us define what is a velocity potential. So this is defined by mathematical function phi. Velocity potential. It is defined by mathematical function phi. Like a stream function, it is contradictory to concept of stream function. This is a phi, and in flow field, this function phi, or you can say mathematical parameter, is in such a way that phi is again function of x and y. In flow phenomena, in defining two-dimensional flow, phi is a mathematical function, hypothetical function, and phi is a function of x, y in such a way in flow field that partial differential of phi along x direction, del phi over del equal to velocity in x direction, that is a u. Here that is a x and here it is a y. So velocity in magnitude of velocity in x direction, because here this potential function is a scalar quantity. So velocity here, u is defining magnitude of velocity along x direction, and v defining magnitude of velocity along y direction. So partial differential of this function phi along y direction gives a value of magnitude velocity v along y direction. So this is a contradictory to psi. Del psi over del x equal to minus v, and del psi over del y was equal to u. So it is just, you can see, opposite of the concept of the velocity potential. And we know that this function is this parameter phi is a function of x, y, so we can determine exact differential of phi, total differential of phi. We know that phi is a function of x, y. So total differential of phi, d phi equal to del phi over del x dx plus del phi over del y dy. This is a exact differential, total differential of the velocity potential phi, and we already know this is equal to u and this is equal to v. So d phi equal to u dx and plus v dy, which is u. And for constant velocity, for equipotential lines, phi remains constant. Phi will remain constant. When potential is equipotential means phi remains constant. So d phi equal to 0. This will become 0 for equipotential line. So u dx plus v dy equal to 0. So dy by dx at phi equal to constant equal to minus u by v. This is a for the equipotential line. At equipotential line, slope or gradient of the line is equal to u by minus u by v, minus u by v. And from the constant, for constant stream function, d psi equal to minus v dx plus u dy, that is equal to 0 for constant when psi remains constant. So from this equation, 0 equal to minus v dx and plus u dy, dy by dx here, dy by dx equal to v upon u at psi equal to constant, at psi equal to constant. So this is a, by combining both, because at phi equal to constant for equipotential line, dy by dx, that is equal, you can say m1, and here you can say it is a m2. Here you can say it is m2. So dy by dx at phi equal to constant equal to minus u by v, and dy by dx at psi equal to constant equal to v by u. So multiplying these both, multiplying both m1 into m2 equal to dy by dx at phi equal to constant multiplied by dy by dx at psi equal to constant equal to minus u upon v into v upon u equal to minus 1. And this is the condition of orthogonality. This is condition of orthogonality of these two functions. Phi means constant equipotential lines and constant stream lines, and stream lines both intersect at 90 degrees. This is the condition of orthogonality when two slopes, product of two slopes that we have studied in geometry and mathematics, that when product of two slopes equal to minus 1, then these slopes are intersecting each other at 90 degrees. This is the condition of orthogonality. So this we can show in a graph. We can show in this way. This orthogonality we can show here. Suppose this is, these are psi equal to psi 1, psi 2 and psi 3. These are extreme lines, and these are equipotential lines, phi 1 and phi 2, phi 3. These are equipotential lines. These are intersecting when we take slope of any one, slope, another color, using another color. So slope of this line and slope of this line, both will intersect at 90 degrees. This is the condition that we have shown here, that the slope of equipotential line and slope of stream lines, constant stream function lines, intersect at 90 degrees. This is very important conclusion we can draw. How, and drawing these lines make a flow net. See, this is known as a flow net. This one is known as a flow net, and this can be used for the defining complex nature of flows from different types of the flow channels. So this significance we can discuss here by solving a problem. How we can solve problem by given value of psi, we can find from psi to phi and from phi to psi. This we can take by one example. So let us solve one example to make our concept more clear. What is the meaning, how phi and psi are interrelated, and what is the physical significance of psi and phi. So let us solve one question. The question here is, check whether the flow is defined by the stream function psi equal to xy is irrotational. This is a psi given psi equal to xy irrotational. If so, if there is irrotational, then determine the corresponding velocity potential, because we know that if flow is irrotational, in that case for rotational flow potential is 0. Velocity potential is always 0 for rotational flow, but for irrotational flow, when flow is irrotational, then there is a velocity potential exists. When flow is irrotational, only in that case velocity potential will exist. Means if something is rotating, it will not go ahead forward. It will not go forward. So rotational things are not having any potential to move forward. That's why when there is a potential, then it must be irrotational. flow must be irrotational for condition of the having velocity potential. So one of the condition of the irrotational flow is for three-dimensional curl V. Curl V equal to 0. Curl V equal to 0. Or you can say for two-dimensional flow in x and y direction, W z rotation about z axis equal to 0. Or simply you can use another equation, del square psi upon del x square plus del square psi upon del y square equal to 0, then flow is irrotational. If this condition satisfy, any condition you can satisfy for two-dimensional flow, if any one condition satisfy, then flow is irrotational. So here you can check it, del psi over del x, psi equal to 2xy. So del psi over del x, del psi over del x equal to 2y, and del square psi upon del x square equal to 0. Similarly, del psi over del y equal to 2x, and del psi over del square psi over del square y equal to 0. So putting this condition, 0 plus 0 equal to 0. So this condition satisfies that flow is irrotational. This means that velocity potential will exist. Certainly velocity potential exists for the irrotational flow. And now we have to find out phi. When exists, then how we can find out phi? We know that phi equal to d phi equal to u del phi d phi equal to del phi over del x dx plus del phi over del y dy. These are velocity u dx plus v dy. Already we have discussed it. And what is u? U is a del psi over del y, that is equal to 2x from given equation, psi equal to xy, and v equal to minus del psi over del x, that is equal to minus 2y. So putting here values, u equal to 2x dx minus 2y dy, that is equal to d phi. Now for finding out phi, we integrate. So integrating this one, d phi 2x dx integration minus 2y dy integration. So phi equal to 2x square by 2 minus 2y square by 2 plus c. So phi equal to x square minus y square plus c. So this is a velocity potential we have derived by given condition of psi equal to x. This is the simplest question. Just I solved it just to interrelate how phi and psi are interrelated, but you will always get simple question for GATE examination or IAS examination in such type of question. Not very tricky integration will be required, but you will get some tricky question where you have to manage how to integrate d phi. So you have to manage here these quantities in right side in such a way that you can easily integrate, because sometimes this number may be very complex. You have to manage it so that integration will not go wrong, otherwise the answer will be wrong. So I think this is very useful for you to understand the concept of velocity potential and stream function. Both are interrelated and both are contradictory in terms of the concept, because we have used that phi is such a function that partial derivative along x direction with respect to x will give velocity along f direction, same velocity, that is u, and partial derivative of velocity potential along y direction with respect to y will give velocity along the y direction, that is v. And that concept is opposite for the stream function. Partial derivative of stream function along with respect to x will give velocity along y direction, that is negative, and partial derivative of the stream function with respect to y will give velocity along f direction, that is u, and that is positive. So that's why both intersect perpendicularly. So this will make a flow net. So this concept is very useful from competition point of view. One question you often get in GATE examination and Indian Engineering Service examination and so many public sector examinations, and I think you will like it and subscribe it and share it to your friends, and you can also ask me particular topic on which we can make a video lecture. Thank you very much and have a nice day. Thank you.